Most welcome to Donsö and Donsö Safety Meet and the seminar on future fuels and their safety aspects. We will, during this morning / over lunch session, pass through 9 options for us in the future for energizing our vessels. We will try to focus on the safety aspects because that's what keeps this program together. This will be a bit of lecture style, so not so much questions and discussions. Instead, we do in Safety Arena in the afternoon from 2 o'clock onward in a separate schedule. So this will be a little bit monologue style with a little bit tight schedule. But we do it in 3 blocks with a small pause of 10 minutes and then the second pause being a little bit longer, 20 minutes, for going out and finding some refreshments. And to keep it all together, we have Mikael Johansson from DNV. So I will just hand over to you, basically.
Thank you, Martin. Warm welcome to everyone. It's a great pleasure to be here speaking at the Donsö Shipping Meet. I have been giving some presentations over the years at this great venue, so it's nice to be back and that they want to have me back. As Martin said, my name is Mikael Johansson. I work with DNV Maritime Advisory, heading the Swedish and Denmark branch of the unit. I was here, I think it was over 10 years ago, with the introduction of the NOx and SOx regulations, talking about that fuel transition. So today, a little bit similar, but in a quite beefed up version of that session. If we look at where we are, we will change dramatically, both shipping and society at large. It is a truly big shift that is undertaken. We know now that over summer, the marching order has become even louder. We have to move even faster. And I think the session today is about how do we get there, and how do we get there in a safe manner, and what are the options at hand. We are debating, I think all of us, debating quite heavily the different options that we have, the different challenges that we have ahead of us. There is a vast number of alternatives that are discussed. I think basically all of those alternatives will be handled and discussed here today in both the presentations as well as the discussions that we will have afterwards. The different roadmaps, the different economical challenges, the raw materials is something that is high up on the agenda. I think the focus for this session on the safety aspects of these new energy carriers is a vital question that maybe we are not discussing to the extent that we should. And I think that is why this sort of venue is highly welcomed. As stated, successful uptake of alternative fuels requires a lot of pieces of puzzles to fall into the right place. And as highlighted, some of these areas, like cost, availability, etc., that are natural pieces, are heavily discussed. Today, we will focus more about the knowledge aspect, as well as the regulations aspects. How can we reach the targets that we've set in a safe and practical manner? We also know that even that some believe that it's taking a bit too much time, we know that there is a big uptake in terms of new and different energy carriers compared to what we're used to. We also see that from this picture, the safety aspect will of course change. We were used to having a reality where all ships basically were handling one type of fuel, one type of energy carriers. As can be illustrated here, already today a number of different options are used within shipping. More options are discussed. Obviously, this will have an impact on how we manage safety and that we do this in a reliable manner. This will not affect only the vessels, it will affect the entire value chain. It will affect the guys and girls working on board the ships, as well as the guys and girls working in the offices, managing bunker and also doing the production and handling of these various fuels and alternatives that we have in front of us. As we see, this is just a small overview of differences of the various fuels that we are currently discussing. We don't need to go into the details of this. I hope this will be covered in the various topic sessions when it comes to the various aspects to be managed when it comes to toxicity, when it comes to flammability, when it comes to how can we store and transfer these fuels in an efficient manner. So that is the focus that we will keep here today. We also see that any type of setbacks, if we are not able to introduce these new fuels, these new energy carriers in a safe manner, any type of incidents will have dramatic impact on the pace that we are able to pick up new fuels. This is a picture from a hydrogen fueling station from, I think, 2019. These are pictures. If we are to reach the targets that have been set and the targets that we're working towards, these are pictures that we don't want to see when it comes to shipping. These kinds of incidents will make trust in new fuels more difficult to gain, and it will make the time for achieving the change much slower. We also need to see that fuel is not only what we have in the tank. As highlighted, this will impact the entire value chain and the entire work, both in the shipping company's offices and in the work that we have on board, as well as the knowledge that we have in the supporting supplier organizations, rule developers, etc. We need to look at the entire vessel and the entire chain of logistics and understand how is the safety picture impacted by new fuels, by new energy carriers, by new technology. And of course, being from DNV, I have to talk a little bit about rules and regulations as well. Rules and regulations are enablers for introducing new technology in a safe and practical manner. We also see that there is a lot of development going on. We can also see that the technology as it is today is maybe outpacing the rule development. That is a gap that also needs to be addressed. How can we do this fast enough in order to reach the targets that we have set? In addition to that, we also have rules on a global level, we have rules and regulations on a regional level, and of course we have local rules and regulations as well. We all need to make sure that these goes hand in hand and not conflicting with each other. One aspect that we have thought a lot about in DNV is, of course, the training aspect. Working with new fuels and new technology will require new competencies. As I said previously, it will require new competencies across the value chain. But of course, it may be impacting mostly on the seafarers as such. As I said earlier, we were used to handling one type of fuel, one type of safety aspects. Today we are going to cover 9 different technologies. Do I have to know all this? How do we make sure that we have training to address these new technologies? Can we do that change fast enough? Can universities training naval architects, can they cope up with this pace? Can training academies for seafarers, can they manage this development? This is an aspect that is highly relevant to also address when we talk safety in a safety seminar. To sum up and to leave the floor to the people knowing these different technologies inside out, and let them talk about the safety aspect of these new fuels and new energy carriers. I think there are some key points. We talked about the technology moving so fast and new technology being implemented. Making sure that rules and regulations are keeping up pace is key. Understanding that knowledge and education and experience needs to be boosted across the entire value chain is also a key aspect moving forward in this field and to enable the change that we're looking into. Trainers and also, of course, retainment of that knowledge. How do we make sure that the people that we have trained, the competence and knowledge that we have within shipping, that we retain that we keep the maritime industry a relevant and interesting industry to be part of? So these are some of the questions that I hope that we will get good insight to into today's sessions, and can also discuss further during the afternoon in the focus groups. With that, I will leave the word to the first block of presenters. So I welcome you up on stage from
Yes.
FKB, Corvus, and Good Fuels.
And we have Christian Sjöberg from FKB, Carl Björn Berge from Corvus, and Bernard van Herringen from Good Fuels. Floor is yours.
And then I leave the baton to you, Christian.
Yes, thank you. Let's see. If I can get the right picture here. There. So I'm from FKB, been working there for 11 years now with ship design, starting as a system designer, now also being part in the concept and contract design stage, being with the full design process of the ship. Originally, I'm educated in sustainable energy systems at Chalmers, so that's kind of my background. LNG, we can start with what is LNG? LNG is, in its basic form, it's natural gas constituting of mainly methane, propane, and butane, and nitrogen, and CO2 is also part of the composition, but the bulk is methane, it's 90%. In this umbrella of fuels, you also could say that LPG and LSNG should be included because it's kind of the same fuel, even though it has different sources. We have biogas, that's when it's supplied as LPG, is a quite nice fuel. It's better composition in it than the LNG, and you also have the synthetic gas SLNG that can be provided, and it's quite pure as well. So this fuel comes with some risks, as all new fuels come. First and foremost, it's cold. You store it at minus 172 to minus 167 degrees. So if you get it on, you will get frostbites or cold burns. And normally we never use LNG on board because we store it as LNG, but before usage we evaporate it and heat it up to 20 to 40 degrees before sending it to the engines or the other combustors we need. So if we would have an LNG spill, the big danger would be that it forms a cloud of cold and natural gas that will push away all other gases, and you will suffocate if you are in the cloud, or especially in an enclosed compartment. For the LNG as it is, or NG, it's odorless, it's non-toxic, and it's non-visible. So you won't see it, but it will be there. Possibly you see the cloud forming when the water in the atmosphere is condensed. LNG or natural gas has the possibility to burn when mixed between 4 and 15% into air. Otherwise, it will not ignite. So in closed compartments, you quickly reach this level and it will not burn. But outdoors, it will mix with air and you will have a possibility to ignite it. The lucky thing is that LNG that is evaporated to NG is not really burning explosive. It's burning off like a large flame. So radiation heat is a problem, but it will not explode in that sense. But when evaporating from LNG to natural gas, then it will be an expansion with 600 times the size. So the evaporation can be almost explosive. So the LNG is pumped from the crust or the natural gas. We extract it, we clean it, we cool it to LNG. LPG and SLNG are produced in different ways. Biogas is produced by anaerobic digestion of household waste and farm waste. SLNG is synthesized. So when it's liquefied, it's stored in cisterns before transport, and it's transported primarily with ship and to some extent pipeline. Of course, we do actually have some road transport and some train transport as well, but seen to volume, that's not much. Normal transport is from terminal to terminal or ship to ship, and we are most interested in ship to ship since it's how we use it. Normally, we bunker the fuel via bunker station onto the ship. We store it in the LNG storage tank on the deck. And we keep it cold. Normally under pressure to some extent. When we bunker, we make the excess gas either go back to the ship or we increase the pressure and then we flush it with LNG within the tank to cool it down and make it a liquid again and to keep down the pressure. When we take out the LNG for usage, we heat it up in the tank connection space to a temperature of 20 to 40 degrees, evaporating it and heating it up, and then we send it in single-walled pipes back to the engine room area where we start to go enclosed. Here we have master valves for each consumer to be able to shut down a consumer in the engine room before we send it in dual-walled pipe to the gas valve unit that is also serving individual components in the engine room. And the served unit and the served units are boilers and combustors primarily. We also recommend to have a boiler on board that can burn NG. Otherwise, you might need to release natural gas straight into the atmosphere. You can't handle it if you get excessive pressure or something like that. But it's not class rules to have a boiler. So from safety concerns though, what do we look at? We have cold surfaces, we have the fire hazard, we have leakage, we have the environmental parts, and then we have the bunkering process that we need to consider. So cold surfaces, we are talking about a cold media that you cannot touch it. You will get cold burns. So we need to focus on exposed flanks and pipes normally this is mitigated by having either insulation or by putting these pipes in dedicated areas where you normally don't have access, like in the tank connection space. And when you work with it, you use protective clothing. And that would be during bunkering procedures and also during maintenance. The NG piping, it's not that cold, so it's not really an issue with the cold surfaces. Then we go on with the fire hazard then. In a fully functioning system, there should not be any gas that can be ignited. But we have working conditions where there we will have releases. For example, if we have overpressure in a tank, we need to get rid of it. Or we have a malfunctioning engine or boiler, we can have gas buildup in the exhaust gas system that we need to take care of. This is not the failure of the system, but it's conditions, operation conditions that we need to be ready to take care of. The next step is that we actually have a system failure. We have a leakage into the dual-walled piping that we will need to get rid of, or we have a leakage outside that also needs to be taken care of. All likely failures are mitigated. We take care of that. We see that the ventilated air with the gases actually end up at places where we know that we don't have ignition sources. If we have a pressure buildup in the tanks, then we need to take care of that. We could either send it to a boiler, vent it, or as a last resort, we need to jet it on it, as not to blow the tanks. We also need to consider external fires. So if we have a fire on deck, we need to protect the LNG tanks with a water spray system. We protect the bunker stations. All spaces where we have LNG that will expand rapidly, we protect with water spray. Then we have smaller pieces of pipe, like the NG pipes connecting the tank with the engine room. If these burns, it's not good, but it's considerably safe seen to a fire on deck. So leakage then. Leakage could be dangerous since it could fill up a room, making it inert. So people within it would suffocate. In the engine room, we have dual-walled piping that is either ventilated or inerted with overpressure, and then we have detectors to see that there is no natural gas in those pipes. In case we have leakage in the engine room, we either have an emergency shutdown system that will shut down the engine room if we have single-wall pipes. If we have dual-wall pipe and detect gas in the pipes, we will shut off the LNG piping, close the master valve, and yeah. In the case where you have dual-walled piping all the way, you will switch over the main engine from natural gas to diesel and continue operating. In the case where you have emergency shutdown of the room, then you will have a blackout, principally. So, but we need to shut down the rooms if we don't have dual-walled piping. Outside, if we have a damage, then it's vented to the atmosphere. It's the way we have to operate. From an environmental perspective, LNG is generally positive. When combusted, we have less CO2, we have less PM, we have less NOx and less SOx than conventional fuels seen per energy unit. And in the case of leakage, we do not really have any sticky residues that will float around on the sea and cause havoc. We will only have the gas that goes down into water and then evaporates and it's gone. We can't do anything about it. We could see that in Nord Stream, among other things. But when we leak methane, we have great greenhouse potential. So that's potential of 23 to 85 times that of CO2. So it's not really good to release unburnt methane. Going on to the bunkering. A leakage during bunkering, the thing we are most afraid of is to get it on the steel or in between the ships. Because if we get it into the water in between the ships, it could expand rapidly and push apart the ships with damage to the ship's side. Or if it's a large spill, we could also freeze the side of the ship and make it rupture. We also need to consider this in the bunker station. So the bunker station is protected using a stainless steel drip tray, and then we use water spray or a water curtain to protect the side of the ship. We also have breakaway connections in the case the ships are parting, so that the flow is stopped, and we have ESD connections to actually shut off the pumping on both sides and close the valves in the case that the connection is broken. So to mitigate all these things during the design process, we have some tools. We have the hazard, which is the primary safety considerations, where we try to identify risks, we try to evaluate risks, and we try to mitigate the risks to ensure that things don't happen. We also use an hazardous zone arrangement. This shows where do we have gases and where can we expect to see that there is risk of explosion. And then we need to mitigate it. We need to put the places where we have release of gas in places where it's not dangerous, and we need to see that equipment in this area are EX and ATX classed. In closed compartments, we need to ensure good ventilation. We have gas detectors to see that we don't have buildups of gas, and for example in the exhaust gas systems where we expect to have the potential of gas filling, we have good ventilation and we have explosion relief valves if it were to ignite. And as said, bunkering, we have breakaway couplings and ESD connections to be able to shut down the bunkering procedure. There is certainly more questions and more details to this as well, but that's for another meeting. So, thank you.
Good morning. My name is Kolbjørn Berge. I'm from Corvus Energy, working with regulatory affairs, and I used to work for the Norwegian flag state. So safety is of course a big focus for us when we are working on introducing new technologies on board ships. First, just a few words on introducing Corvus. Corvus is located quite widely spread around the globe. We've been in operations in 2009, started in Canada, then moved to Norway to be part of the green transition in Norway when all of the vessels started to go on batteries in Norway. Our sales guys use this slide to some extent to point out other things than I do, but all of these operating hours and all of these projects gives us vital knowledge. So that's something that we need to take good and use good, that all of that experience that we get in the field are transferred back into the products, and also how you install it on board and how DNV, for instance, regulates it. So this is our product lineup. I'm not sure if you guys have seen, you saw maybe batteries yesterday on board the tank vessel. So we have a portfolio of different batteries with different chemistries and different properties. So even though it's batteries, they can also have different properties. So you need to keep that in mind. It's not batteries, it's batteries. It can be different property or different products with different properties. And also fuel cell, but I'm not talking about that. Every time we have a technology transition, we need to mitigate, or we are being introduced to new set of risks and different set of risks. So it's not necessarily higher risk, but we have to face a different set of risk and treat that through the design of the vessel and also through training of the crew. for instance, you don't necessarily use firefighting systems and such on the same manner as you do for fossil fuels, as you do for batteries. So you need to keep that in mind also when introducing new technologies. So when we introduce new technologies, we need to keep every failure scenario as low as possible. We shouldn't let it escalate to affect more of the vessel, and we should keep that also in mind when we are designing new products for this transition, that we need to have a high focus on safety, and we need to keep that failure scenario as at the lowest level possible. And batteries, they have some risks. They can, and in rare situations, have failures due to deviations in production or other defects, or how they are treated on board can ignite a thermal runaway. We try to mitigate most of those causes by having a sound and good battery management system that protects the battery cells for external loads such as high temperature and high voltage, and also under voltage. But still you can have that internal cell failure, and that can escalate quite rapidly. You get gas, you get heat, so it's something that you need to manage. And our point of view on this, at least from Corvus side, is that you need to have a passive system that handle that risk. So you're not depending on other things that limit that incident. You need to build that into the design of the system to handle the risks that the system can cause to the vessel. You need to contain that failure mode. Because if you have a lot of other different systems to protect the vessel from a risk that your new technology introduce on board, you are depending on several other systems that can fail. They can have latent defects, and if you are relying on those and those fail, you are in a pretty bad situation. So we need to have control of these risks. And I stole this from some IMO regulations. You should do this through design. You shouldn't rely on safety through that the new technology you introduce on board is safe due to some operational procedures or anything else. It should be sound and good design that gives the safety to the system and also the vessel. And this is something that we need to do together, because safety is something is not done by one. And when we are introducing all of these new technologies, such as batteries, we need to, it's still new technology. Even though we have more than 800 projects, it's been on board vessels for 7 years, so there are still things that we don't know. And we need to use that learning to improve the safety. Because as Mikael said, if we get huge failures, we will stop the transition. And we use all of that knowledge that we learn from all of our projects to share, and also share not all, but the failures we have, we want to share those with our clients and our ship owners and the regulators. So we openly share when shit hits the fan. So we tell what went wrong. If it was our fault, we will tell. And we also need to give support to our ship owners or our clients that have these technologies on board. So if something happens, they can reach out, we can help them and support them. So basically what we do, we we try to, or we have the single cell propagation prevention. So if you have a thermal runaway, we keep that incident to a single cell. And also when one of these cells goes off, it develops 122 liters of gas for this system. And we have 24 cells in one module. So if you have a system where all of those cells goes off, you would have a huge amount of gas you would need to handle. But also, in addition to having only one cell, we also want to have that gas taken out of the battery room. We don't want to have that gas release into a battery room on board a ship. You have sources of ignition there, you have the batteries themselves. So we want to have that gas taken out of the battery space. So our battery system is enclosed. So if you have a cell failure and all of that gas is released, it's ducted to a safe location outside the vessel and to atmosphere. And yeah, and also that's probably a bit overachieving because the requirements are not on cell level, but we have done experiments and seen what will happen if you release all of the gas and ignite that. And we also need to keep in mind that this is systems that goes on vessels. It's not the same as battery systems that you have in cars. On a car, you have 4 people and you have 4 emergency exits. So it's easy to get out. On a vessel, you need to increase that safety level compared to automotive battery systems because you are on a ship, you are far away from help, and you need to ensure the safety of the crew and the passengers. So we need to have a higher safety standard than on automotive batteries. And also knowing the cell chemistry that you are working with, because there are a lot of different cell chemistries coming into the market. And all of those, even with the same chemistry, you will have different properties. So you need to know the properties of the cell to be able to provide additional safety to that cell. So we need to build a battery management system that protects the cell so the cell doesn't do things that it shouldn't do. And also keeping in mind the lifespan of the battery system. We want to have it in operation as intended. So all of these things are parameters that we need to monitor to ensure a safe battery system, because if you overuse it, if you use it more than it's designed for, with more cycles and all of these, you can deteriorate the cell, so you might introduce a thermal runaway due to that as well. So there are a lot of things we need to keep in mind when introducing batteries. You can have failures or risks that are external to the energy storage system, such as over temperature in the room, fire in the room next door. So mechanical impact, deformation, all of these things are things that can create a hazardous situation with the battery system. So also water, external short circuits, and all of these things are things that we need to have focus on when implementing it on board. And also there are fault conditions that are internal to the battery system, such as internal short circuits creating the thermal runaway. Production faults also can lead to thermal runaway. And also the sleeping faults or latent faults, such as software issues and all of these things that we need to have control of to ensure that the battery system is safe. And all of these things can lead to hazards that are posed by the energy storage system. You can have thermal events, you can have gas emission, you can have electrolyte shock, electrolyte leakage, and electrical shock. So it's a new thing that we introduce on board, and we need to have focus on all of these things when implementing it on board vessels. Because all of these things are something that you get when you get a battery system on board. You can't move away from that. So it's not something that only one stakeholder can manage. It has to be a cooperation. It has to be us as a battery supplier. We need to give input to all of the other stakeholders how to safely introduce these things on board. And the system integrator plays a vital part on how managing the batteries, using the batteries, and how it's integrated on board the ship. Shipyard and ship designer are also key stakeholders in ensuring that the battery system is installed in a safe manner. Of course, complying to regulations and specifications, but also having a safety view on how it's installed on board. Approval bodies and the ship owner and operator. So crew training is something that's vital to ensuring a safe battery system, because you need to keep an eye on different things than you used to do when looking after a diesel engine. There are other external hazards you need to keep an eye on. So the crew training is very important, and that's one of the things that we have seen from the incidents we have had, is that the crew wasn't necessarily sufficiently trained. So they didn't act as they should have done. They used everything they had instead of going in a strategic manner to mitigate the cause. So, thank you.
Good morning. My name is Bernard van Haringen. I work for Good Fuels. We are a marine sustainable biofuel supplier based out of the Netherlands. We're part of the bigger Finco Energies group, and under Finco Energies, we have quite a wide variety of decarbonization services, amongst others offsetting and insetting services, but more also on the physical side where Good Fuels comes into play, where we are actually delivering the fuel. Also looking a little bit more into the future with Good Power, which is based on or focused on sustainable electricity, and Good Biomass, whereby we actually turn biomass into energy. Focusing a little bit more and zooming in on Good Fuels. So we've been around since 2015. 8 years in the running now already. And in the beginning we were basically starting as a pioneer. We created the biofuel market in the marine business that was non-existing before. So a lot of years of testing together with the clients and really pioneering with ship owners that are progressive. A lot of them actually based here in Scandinavia. Through the years now. We've built quite a track record, a lot of clients, a lot of experience, and we really like to also share this experience that we have built with our clients. Since 2021, we've now delivered to 60 different or more than 60 different ship owners, so it's quite a track record, and basically in all different aspects of the shipping industry. Be it container vessels, tanker vessels, dry cargo, car carriers, cruise ships. I would say that in all of those segments we've worked with more than a dozen different ship owners. So the track record is really there. And now, and what is also good to say is that we also provide biofuel as 100% fuel. We've had several clients that have been sailing on biofuels now as 100% fuel for more than 3 years. So. And moving a little bit from the progressive pioneers towards now what is very important is the regulations. Makes our life a bit easier because ship owners need to act. You see a lot of ship owners that are making moves. This is actually a little picture that we borrowed from our friends at the DMV. And it just shows the way that biofuels can be used to control and balance your emission goals. The more biofuels you use, the less or the better your, let's say, CII rating becomes. Makes life easy to really balance that. Of course, the very monumental MEPC 80 was a great step also for biofuels, paving the framework and paving the way for the use of biofuels for your IMO and DCS reporting. Basically, what it says shortly is that if you have, if you're purchasing biofuels that are vetted by a certification scheme, meet certain sustainability criteria, and has a minimum CO2 reduction, then you are able to report this under your CII and IMO DCS. Also, quite a big breakthrough is that there's an, how do you say that? Yeah, an interim guidance. Always forget the word. Interim guidance that approves the tank to wheel approach, tank to wake approach as 100%, because biofuels are then seen as a 100% reduction because of the biogenic origin. Then there was the introduction. Safety-wise, I would say biofuels are in the whole range of all the future fuels available on the very safe side. So that's easy. Just before the coffee break, we can relax. It's not the biggest issue when you're thinking of biofuels, but I'll address a couple of points. Yeah, biofuels is a high flash point, above 100 degrees Celsius, so explosion risk are very minimal. It's a biodegradable product, which is good for environmental purposes, obviously. It's not a dangerous good. It does not contain any dangerous chemicals either. No benzene like for fuel oils. So that all kind of makes life easy for the use of biofuels, and yeah, with that it's a very easy way to implement and to make a decarbonization effort. Yeah, important things are storage and shelf life. I think those are two items that for operational continuity are important to know about. When it comes to storage, it's important to know that you will need to have tank heating for biodiesel. The fuel needs to be stored at a continuous temperature. It's about 10 degrees above CFPP. CFPP lying around 8 and 15 typically. So yeah, that's important to notice that it will be heated at all times. Shelf life is a question that we get quite often. How long can you store it on board? We recommend for 100% fuel maximum 4 months, which gives you some space. We've done quite some tests also with different clients, whereby we have actually tested it after six months. What can you do to, and that all went fine. If you are not certain about the compatibility, the homogeneity, the working of the fuels after 6 months, we can always do a spot test and see if it's indeed still good. And this is for 100% biofuels. If you're blending, like making a B30 blend, then you can easily also store it up to a year. Or when you're looking at renewable diesel, you can even store it for much longer. Yeah, I think it's very just important to, as a ship owner, look at providers of biofuels that know what they're talking about, that have done their technical assessments, have done their testing of the fuels, both in test beds as well as on board. And also maybe good to touch upon is the emission testing. So biofuels have virtually no sulfur, so that makes it easy for sailing in SECA zones. And the NOx test that we have done show that it's somewhere between the values of gas oil and heavy fuel oil. Yeah, this is a little bit of a point that kind of contradicts with the easy safety nature of biofuels. It relates to the IBC code, so the International Bulk the bulk chemical code, so the usage of chemicals on board a barge. Yeah, so MARPOL dictates that when you have more than 25% biofuel on board, the fuel is seen as a noxious liquid. So the treatment should be done as if it's a safety and environmental hazard. Meaning you need a very different type of barge than the fuel providers actually have on board or have in their system right now. And that makes it a little bit difficult. So if somewhere around the world you want to deliver more than 25% biofuel, you would need to have a completely different barge, namely a chemical tanker. And if you now look at Europe, whereby this is not the case, because over the years we've now seen that there has been an agreement in Europe for inland barging, whereby it's allowed to have 100% biofuel in your barge. So, like in countries such as the Netherlands, which is the biggest port for biofuels so far, you can just deliver 100%, and there's no limitation on the uptake. Looking at another big port like Singapore, you would have to limit up until 24% biofuel. That being said, it shows that the track record is there, that from a safety perspective, it's not difficult to deliver more than 24% up to 100%. So the big question to the IMO is, why are we still limiting this and limiting the uptake of biofuels outside of Europe? Availability is always an important part of the question as well. Of course, when you want to opt for biofuels, you want to know that there's some operational continuity. So where can you get it? That's still a problem, I would say, for the shipping industry. Major markets, as I said, are still in ARA and in Singapore, but you see more and more suppliers popping up in smaller locations. Also, I think this is very much to be attributed to CII, whereby, of course, you can't just on a mass balance use biofuels and decarbonize, but you actually need to per vessel, of course, get a lower rating. So if you're sailing in West Africa, then you have a very difficult problem at hand because there's not a lot of biofuels available. Yeah, how do we mitigate this? Well, at Good Fuels, we are already trying to grow. So we're in Europe, Singapore, in the US, and also have some experiences in other places in the world. So yeah, start a dialogue with your provider. Can you be delivering at location XYZ? And when there's enough demand, of course, it will pop up immediately by itself. Yeah, and then what of course helps is governments and authorities that incentivize biofuels. And lastly, this IBC code that I was talking about earlier. Yeah, availability is of course not only location, but it's also the availability of feedstocks. Another nice graph from our friends at DNV here, which shows the expected fuel mix for 2050. In green, you can see in 24 different scenarios what the role will be that biofuels will play. So that being said, will there be enough volumes to serve all of this green part of the shipping industry? Now, we've done, of course, our own research. On the short term, we really don't see this problem. The demand doesn't meet the supply at all yet, so there's a lot of room to grow. Looking a little bit more further into the future, 2050, we've done our assessments looking at waste and residue streams. Of course, you only want to have the sustainable biofuels, and then allocating the amount of available feedstocks to the marine industry. we've taken about 1/4. So of course, there's also feedstocks going to aviation, and there's feedstocks going to the road. So all in all, we expect to have available 21 megatons of biofuel in 2050, whereas the expected demand, looking at that slide we just looked at from DNV as well, in a big study, we're only expecting 16 megatons in 2050. So we should be in the clear on that side as well. Last point I want to discuss is sustainability and transparency. Super important now that the biofuel business is growing. How do you make sure that you're actually buying a sustainable product? We've seen early in the year, some fraudulent feedstocks coming from China. Big problem, of course, and it makes the whole biofuel business look bad. So what do? You need to select a supplier that has done its due diligence, that knows its own suppliers and has a good idea of the whole supply chain. And then of course it's important that the supplier is also ISAC certified or RSB certified. But that doesn't quite cut it yet, because there's much more things that you actually would need to look at to make sure that you're really buying a sustainable product. At Good Fuels, we've put this out there for ourselves, and I think it's also important for a client to sit together and think, okay, what is really important for us when we're buying biofuels? What sustainability criteria do we want to hold our providers accountable to? At Good Fuels, we're only working with waste and residue streams. The feedstock may not compete with the food industry, and it cannot lead to deforestation. And then we have an independent sustainability board that's constantly scrutinizing these feedstocks and making sure that they're actually sustainable. So that's something that ship owners could also think of, making some kind of system like that. And then this is looking a little bit more into the future. These are a lot of tests that we're doing at the moment to basically map the origins of the feedstocks. We've done now 3 different tests, one recently with GCMD, so the Global Maritime Center for Decarbonization in Singapore, for fuel tracing. You can do fuel tracing both on the physical side as well as on the digital side. On the physical side, what you do is you put an isotopic trader into the fuel at the beginning of the supply chain, and then you can follow the marker until the end of the supply chain, and you can see exactly where it came from, how much it has diluted. So the application of that is that the more and more players in the whole supply chain that become part of this system, the more and more traceability we will have for the actual origins of the product. Then as well, we have the digital side of the fuel tracing, which is more related to blockchain technology. So with that, you will have on a platform, you will be able to see exactly where the product that you bought from is coming from. And that will lead to a lot of transparency, which of course will be key in the coming years. Proof of sustainability is something that you're seeing. This is the document that's being passed on throughout the supply chain. Also super critical to know that the origin of the feedstock is sustainable. Lastly, just a little call to action. Of course, we all heard the alarming IPCC report last March. Just another report, and our call to action is always, instead of always talking on these conferences, let's actually do something. And I speak to everyone's responsibility to act now and decarbonize. That's it. Thank you.
Thank you so much for this first block of let's say lectures for you. These topics will be discussed at 2:15 in the safety arena in Hall C later on, so almost welcome. And this block contains wind, ammonia, and methanol. And on stage we have Emil Kotz from Oceanbird. We have Tony Stojewski from Wärtsilä and Per Stefensson from Stena. So the floor is yours, starting with Emil.
Thank you very much. My name is Emil Kotz. I work for Oceanbird as a customer product manager. And I'm not only here to represent Oceanbird as a company, but also the wind community in general. And we are all very pleased and grateful that wind is being recognized as a fuel. I have some slides of Oceanbird. We are a joint company between Alfa Laval and Wallenius. We are our own entity. We have been up and running for 2 years now, and we are about 20 full-time employees based in Stockholm. Our vision is to reduce a lot on a few. You might have seen the sailing or sail concept, but we'd like to reduce even more from a lot, that being the retrofit potential that we have on the fleet and also the new build segment. We are a wing sail provider. This is our first product that we are working on, a wing sail that's 560 square meters. We have in-house development of mechanical automation and hydraulics, and our unique system being that we have the out of operation in the tilted state. So we would like to lower the design loads on both the wing sail and the vessel itself. And we just recently were approved or granted an approval in principle from DNV. Later this year, we will start the assembly process of our land-based prototype in Landskrona. And next year, we will have a seagoing prototype or seagoing test rig on board Wallenius Wilhelmsen's vessel, Tirana. But we are not the only provider out there, and there's a wide range of technologies. We also have the rotor sails that's been up and running for 12 years by Norse Power. It's basically large spinning columns that utilize the high RPM to induce the Magnus effect to thrust the vessel forward. We also have soft wing sails. The difference here is that they have the membrane made out of soft fabric, so you can allow the wing area to be reefed in order to reduce the loads. You also have the ventilated foil systems. Here you utilize fans in order to suck the boundary layer around the wing profile to make a more stable and efficient flow. Rotor sails and suction sails are very efficient if you look thrust per square meter, but they are also the ones that require the most energy in order to operate them. And it's important to highlight that the largest products within this portfolio can produce the equivalent of 3 megawatt of main engine power. So if you put a few on these on any type of vessel, you could basically sail. This might be trivial to some of you, but where does wind come from? You know, you have different heating of this Earth's surface due to the tilting of the Earth. So if you look at the different latitudes on Earth, you can see that along the equator, you will have the air with the most heat. So that will be the low pressure area. And in the polar zones, you will have high pressure area. And air tend to go from high pressure to low pressure. And once it's been heated up, it will rise up and recirculate back. In between 30 and 60 degrees latitude, you will have the same phenomena, but in the other way around. And this will happen all along the longitudes of the Earth. And if you look into the polar zone, you can see that air that go from north to south will tend to go to the right due to the spinning of Earth. That's what we call the polar easterlies, and you will see the same phenomena in the tropical zone, and also known as the trade winds. And in the temperate zone, we have the westerlies. So that's the global pattern of the wind. If we look into more detail, what happens from day to day, you can see that wind changes quite a lot in both magnitude and direction, right? So it's hard to predict where the wind will be. You can see that pressure is basically moving all around the northern Atlantic. If you break it down and look at wind as an average from year to year. We had 2010, 2015, and 2021. We can see these global patterns being the trade winds and the westerlies. And in the area in between here, you basically have no wind at all. Back in the days, that's where they dropped the horses in order to have some water left on board. So that's called the horse latitudes. Sailors would basically get stuck there. If we study a route along the northern Atlantic and look at the probability of wind, both in the true wind speed and true wind angle, we can see that the distribution is quite similar from year to year. So what can we conclude? Well, from day to day, the wind is changing quite a lot, but it's reliable from year to year. We know well enough how much energy there will be out there. Wind can reduce the operational expenses of the vessel. We don't have any emissions, and it's future-proof. We can be combined with any fuel that's out there. We don't need any additional infrastructure. Wind is basically the free fuel. That was the pitch, and now we can go into the safety challenges. So, independent on what kind of equipment you put on board, you would need to ask yourself, how do you ensure that your out of operation state is reached, right? For a traditional sailing vessel, that would be lowering the mainsail. Well, if we jump into a scenario here, we look at the wind, how it's picking up over time, the magnitude. And then I'm doing this a little bit quickly. And then we have 3 different products here. Starting in the bottom, we have a rotor sail that's non-tiltable. Okay, what do you do in order to get it out of operation to that state? Well, you basically turn it off, right? You stop spinning, and it's just standing there. The advantage is that it's super simple, but you will have drag once it's standing up. For a reefable, non-tiltable wing sail, at a triggering point, at a certain magnitude of wind, you will start to reef the wing sail in order to reduce the loads. And you will have it standing, just the frame itself. So it will be very low weight, but you will have the operational expenses of the soft fabric that you're using from year to year. From a tiltable wing sail, you have normal operation until you hit your operational window, and then you start to fold and then tilt it down. The advantage is low center of gravity and small ladder area, but you need a high capacity hydraulic equipment in order to ensure that you can do this procedure in all types of winds, right? These are just some advantages and downsides, but I would like to emphasize is that there isn't one product that suits them all. It's all dependent on what kind of segment you look at, where you operate, what trading speed you have, and your cargo handling on board. So it's quite complex. But back to the question, how do you ensure that you reach this state, independent of the solution you have on board? Well, one very effective mitigation is the failure mode effect analysis, where you basically go from the bottom up. You look at every component that you have in your product, the function, its subsystem, and you imagine that you have a failure. What is the cause? What is the effect? What is the severity? And how do you mitigate this? If you do this with relevant stakeholders, you can find things that you wouldn't find otherwise. One thing you can also do is to get real wind and environmental measurements and put it into a simulation model. Here you can see in the green, you have the apparent wind speed that is picking up over time. Until you hit the blue line, you have what we call normal operation. Once you hit the blue line, you will need to fold your product. And once you hit the red line, you will need to tilt it down. So with these time simulations of real environmental data, you can learn your system. You can get insights on unpredictable events, and you can teach it. Very effective method. Another safety challenge is the impact that your product would have on the vessel, and it's very vessel dependent. It's a function of where you place your unit in regards to the size of the vessel and your operational levels. But what we can all conclude is that the wind propulsion unit cannot only deliver thrust, it will also deliver side force, right? So it will impact the leeway and the rudder of your vessel. Here is a simulation case done by RISE. They have looked at a standardized vessel and they've put a VPU close to the bridge. And it's a time domain simulation. So you can see that it's starting out with 8 knots of forward speed. Its only objective is to keep the course, right? To keep the track. But you can see over time that the rudder angle is just increasing. And when that happens, the resistance is increasing and the speed is reducing. So this is a good example of poor balance on board a vessel. This needs to be studied in detail. How can you do that? Well, we can go into very complex method or simplified, but here are some examples. You can perform model tests. Down to the left, you have a 7-meter model by KTH. They've performed zigzag tests in the Stockholm archipelago. This can be compared with more stable environmental tests down to the right that's been performed in-house at RISE, where they put on fans in order to simulate the forward thrust of a wind-powered unit. This data can be used for putting up a simulation model, but also to develop the control system and to be used by crew for training. Lastly, we have the influence on stability and comfort, and it's a trade-off here. For naval architects here, you can see that you have a GM versus draft curve, and that for all loading conditions, we are fulfilling the criteria. But what happens if you put on 4 large wind propulsion units? You can see that we are not fulfilling all criteria anymore. So as a naval architect, what would you do? Well, the simple answer here would be that you need to increase the GM of your vessel. But is it really that simple? Here you have a PhD student at KTH performing roll decay tests. It's the exact same vessel. The only difference is the position of the wind propulsive units. Either it's in center line or 90 degrees. And what will happen? You can see that it has significant impact on the roll amplitude and time until you have stabilized it. So it's not just as simple as looking at one parameter. You need to study everything when it comes to crew and cargo safety and systems on board. So to summarize it, what kind of mitigations do we have? Well, perform continuous FME and hazard analysis to identify areas in your system that needs to be further investigated. You can develop simulations and train with measured environmental data to predict unpredictable events or to teach the system. You need to involve stakeholders early on. That could be the crew, could be the flag state, could be DNV. And for vessel designers out there, you need to allow for vessel design iterations in order to look into all of these aspects and design a really good vessel. Thank you.
So, ready for next one? Yes. I work for Wärtsilä for 23 years and we are known for manufacturing engines. But today I will not talk about the engine so much, but talk about safety around the new fuel, which is ammonia. And I will not speak so much about why ammonia. I think it's well known in the industry. It's the question of if it's answered. It's not going to be if. It's more about when. And why is the answered by the actual decarbonization need in the marine industry? So I want to say that ammonia will be a fact in the marine industry. It's not going to be if it comes, might be, so on. In a couple of years, ammonia will be marine fuel. So what do we need to do in order to prepare for ammonia as marine fuel? That I will try to explore today, not to 100%, but it's a good start. Why do we talk about safety when we talk about ammonia? And the main reason is toxicity. Ammonia is highly toxic. It's toxic to humans to concentrations as low as 300 ppm. That's 300 parts per million. It's nothing, but it's still very, very toxic at that level. You can actually smell ammonia already at the levels down to 5 ppm, which are not harmful in any way. 30 ppm is approved for concentration in which you can work for 8 hours a day, but it's still gonna smell. So the good thing is that it's highly toxic, but our nose, the best sensor we have, it's gonna discover the concentration pretty fast. These levels of toxication are way below the lower explosion limit levels. So today I will not talk about ammonia fire hazards, because ammonia is the most inert fuel used or to be used in marine fuel as marine fuel. It's really hard to ignite. The out ignition temperature is around 650 degrees. So in that sense, it's easiest from a fire risk hazard, but the toxicity is the main risk we have. When you are exposed to ammonia and you don't have personal protection gear, you will get irritations in your nose, you will get irritation in your eyes. Ammonia binds to fluid in our body and then starts to cause irritation and destructions of tissue. So it's really dangerous to be exposed to ammonia, and this is why we need to be very careful. On the other hand, it can harm us in so many ways, but at least it will not give us a cancer. So some positive about this as well. We have been using ammonia since 2021. So we have built operational experience with ammonia for 2.5 years almost in on different engine types and in different facilities. Here we can see our test facility, what we are using in Norway on Stord Island. And together with the Catapult Center and other partners, you can see here, we have established a testing facility with a Wärtsilä engine. This is a 34 DF engine. It starts from a gas platform. We heard this morning so much about LNG from Christian, and we can only say that there is a really good baseline from the LNG industry. There are procedures, there are technologies that could be applied more or less directly, and they are identical to 95% plus. We can use that, and then we can build on that and add the additional safeties for ammonia. So this is a gas engine to start with, and we use this engine in a facility where you can see we try to simulate a ship. So from the bunkering station where we can bunker liquid nitrogen to a tank, and to the fuel supply, and here in the middle we have control. We also have connection to the electric grid, and then we have the ammonia engine in front, and we also have the full exhaust after treatment processing. So this engine have been running on ammonia for 6 months, and we have planned to continue run ammonia for another 6 months at least. One of our test facilities. We have one more test facility in Finland where we test 2 other different engine platforms as well. So we are testing ammonia on 3 different platforms. What have we learned then? We learned that we can use ammonia as a fuel in marine application. We have been having good results with up to 90% of ammonia share on certain loads, but it's not as easy as it may sound. It has challenges to use, but we have achieved at least 85% ammonia energy share. So we can replace 85% of the energy of the conventional fuel with 85% of ammonia, which then does not have any carbon. So it's a carbon-free. A lot of discussion have been about nitrous oxide, laughing gas. This is a high potent greenhouse gas. It has a potency of around 300 compared to CO2. And here we have that we can manage the nitrous oxide emission to below 5 ppm at the exhaust. So really good results. I think with this setup, we can also say that we lower the CO2 emissions by 80%. So this is what we are happy with. You will need, we need to have an SCR in order to handle the emissions from ammonia. So when you burn ammonia, you will have a different type of emissions. You will have unburned fuel, which is, ammonia is very inert and it's hard to combust to 100%. So there will be some ammonia slip, you will have nitrous oxide, and then you will have laughing gas. And all of this could be handled in the SCR. If you look into the same facility, this facility can also be used as a training facility for the future ship owners, where we can train both bunkering and other operations. The first bunkering we did by truck, or it's only possible by truck because it's a land-based facility. We did the first bunkering after working hours in the evening, and it was, you can see from the pictures, our crew, they were equipped with a full PPE clothes or equipment. And then the driver just had this, his yellow overall, and then connected the hose to the bunker station. So what we can say is that ammonia is a commodity. Global production of ammonia is equal to 170 million tons, and this ammonia is transported worldwide. So there are established procedures and safety requirements and standards for using ammonia as a cargo, using ammonia as a chemical. What we need to do now is establish bunkering procedures and safety procedures for using ammonia as a fuel. So good base, bunkering went well. There was no leakages during the bunkering process. Everything went smoothly. The first bunkering, but if you look at the engine side of the equipment, here you can find a couple of potential points where you can actually have leakage from ammonia. You can have leakage to the exhaust gas, you can have leakage to the crankcase, you can have leakage to the liquid fuel system. So we need to equip the engine room with various detection sensors in order to be safe and detect any potential leakages. During testing, we have had a couple of minor leakages. So during the first testing, we had minor leakages mainly due to the wrong materials in the system. Some O-rings was not feasible or not good for ammonia. And then we also had some faulty valves. Once we handled these teething problems, then we did not have any more leakages on the ammonia system. Also the sensors in the beginning, they were detecting 100 ppm, but once, because we could not smell and could not detect ammonia leakages, once we investigated further, it was found that the faulty readings on the sensors were there. So a lot of teething problems in the beginning, and of course there will be teething problems in the application on the first two ships, but no major ones from what we could see. Okay, and now I cannot change the slide. Yeah, okay, good. Ammonia likes to bind to other liquids, to moisture specifically. And when you use a dual fuel engine where you have the ammonia gas injected in the Otto cycle, you compress that ammonia, and some of that ammonia will pass by the piston rings and piston and go down to the crankcase of the engine. And in this case, ammonia will most likely bind to the lubricating oil in the engine. And this is what we also have observed. We took samples of the lube oil, and tests confirmed that there was a very small amount of ammonia. However, there were no changes of properties of lubricating or lubrication oil. The engine operation was smooth most of the times. As soon as we had the first challenges was to adjust the pressure and the temperature of ammonia. So you need to feed ammonia at a certain pressure because ammonia have much lower energy density. So you need to get much gas inside the engine. So the pressure was something that we work as a parameter. And then of course the temperature, as colder the ammonia, then it might condense and then it could be a liquid or it's hard to ignite as well. And then in the high pressure system, which we also test, the mix of ammonia and diesel and then mix of ammonia and gas ratio was something that we have been having challenges in the beginning, but now those are overcome and the engine is running very smoothly. As mentioned, the other challenge is to keep the ammonia either in gas or in liquid, depending on which system you use. The tank might be located in one location on the ship, and then you might have 40-meter pipes until the engine. So you need to make sure that ammonia does not condensate if you're using gas system before the engine. So heat trace on the ammonia supply system is probably going to be needed depending on the length. What more we have learned? During normal operation, we are using the same principle as for the LNG. The engine room is the gas safe space. Everything is double vault. Everything is monitored. Ammonia detectors, gas sensors are installed in all the locations where you can expect leakages. And we have been running in two different modes, both the auto combustion mode and we have been also running with high pressure liquid. That's a bit still in the research phase. We believe that the gaseous ammonia would be the first product to the market, and then the liquid ammonia would be the second product to the market. As mentioned, hundreds of ppm of ammonia was measured evaporating from the hot lubricating oil. What this would mean is that when you run an ammonia and you stop operation, then you cannot go and open up the crankcase and start doing any repair work on the engine. You will need to monitor for ammonia content in the crankcase, and the crankcase is ventilated, so sometime you'll need to pass, and that ammonia will need to be ventilated out of the crankcase. The personal protection equipment is really important, and this is where the safety trainings and procedures should be in place, and these are the ones that we are developing now based on our accumulated knowledge and learnings from the testing. So even if no major leakages have occurred during our testing in both of our facilities, some small ammonia leakages were there. So you can expect that some ammonia might be leaking to the engine room as well during operation, and this is why the personal protection equipment is really important, and as well other safety measures like ventilation and the detection of ammonia leakage. Additional design elements are required, especially when it comes to materials. So as an engine manufacturer, we are taking a lot of research into what kind of materials we can use and what kind of materials are approved for ammonia. So stainless steel is of course something that we use throughout the system, but all of the connection points cannot be just rubber elements or O-rings. It needs to be special elements which are adapted for ammonia. How am I on time? I'm out of time, okay. I'm out of time. I kind of guessed, okay. In the shared presentation, there will be a lot of more material, and I hope you can reach out if you want to learn more about Let's Talk after this. Thank you very much.
Thank you.
Vilken är det? Är det framåt? Ja. Men. Jaha. Ja. So, hello everybody. My name is Per Stefansson, and I'm representing this technological or the technical department at Stena Technique. And I'm going to tell you a little about, well, first the background of methanol and why we're using methanol in this beautiful ship, Stena Germanica. We were actually the first ones that converted a big ship to methanol. And so I will give you a little background about that, and then we come into the safety aspects in the end of the presentation. So, why methanol? Well, it started more or less in 2010. That was when the new sulfur regulations were decided, and we had this so-called sulfur emission control area here in the northern part of Europe. And we realized that fuel costs would increase with about the double when changing from heavy fuel oil to gas oil with low sulfur. So everybody was looking into this, and everybody was saying, well, but you have LNG, so that's no problem. You just run on LNG instead. So we started some research projects to see how possible it is to run on LNG with the existing ships. And it proved that would be extremely expensive to convert ships to LNG. So we started to look into, aren't there any other alternatives? And then we found one of the alternatives, and that was methanol. And at that time, it was, of course, we were hunting the sulfur, and we were hunting the NOx, the nitrogen oxides, because that was also a new regulation that we should lower that from the shipping. Now it had shown that it was a good choice with methanol, also when it comes to carbon dioxide, because you can make methanol from a lot of different sources, and of course also biosources and electricity and things like that. So the reason in the beginning was, as I said, it was a clean fuel, no sulfur and low NOx. And then we realized that it is much easier to handle than LNG because it's a liquid. So we can have it in tanks, and we can pump it and so on, and we don't have to lower the temperature to minus 167 and so on. And at that time also we saw that the methanol was actually cheaper than gas oil. Now prices, as you know, on both oil and on other fuels have been going up and been going down, so you never know really where you are. The cost of conversion to a ship was about a third of the conversion cost of LNG. So this was the reasons in brief for why we choose methanol. Some characteristics, well, I mentioned one that is really a very important characteristic, and that is that it is not a gas, it is a liquid when it is ambient temperature. And that makes the whole life much easier. Everybody's talking about the KISS nowadays, but when we talk about KISS, it's the keep it simple, stupid, because that's really what was one of our goals with this, was to do it as easy as possible. The flashpoint is, of course, a low flashpoint fuel, so you have to use the regulations for low flashpoint fuels. And so that means the increased fire risk, and that's what I will come back to of course, later. On the other hand, it's a high self-ignition temperature, much higher actually than on, for instance, diesel oil. Here it's 464 degrees, and diesel oil has like 280 or something. So it's not a big risk that if you have a drop of methanol on the heat surface that it should start burning. That's not really the case. clean exhaust gases, as I said before, and also environmental friendly. What do I mean with that? Well, this is actually a picture showing how toxic for the environment different fuels they are. And this is actually the bubble showing that how much methanol you can have in the water before half of the fish, they call it the fish tests, is when half of the fish dies in the kind of tests that they do here. It's not really fish, it's some other kinds of microbes and things like that. But if you compare that with for instance, heavy fuel oil or with diesel, it's 240 times less toxic. So it's actually, methanol is actually used in cleaning facilities to clean wastewater and so on. So that is something I think that not very many people knows. When it comes to the regulations, I mentioned that we have to consider this as a low flashpoint fuel, and therefore we have to use the IGF code for the IMO regulations. And there, unfortunately, the IGF code was first developed for LNG and gases. And then when that was ready in September 2015, the correspondence group continued to develop for low flashpoint liquids. So that meant that, and that was the same team more or less, the correspondence group. So that means that a lot of the safety barriers and things that was developed for gas somehow also came into the regulations for methanol and for ethyl alcohols also. So this I think was quite unfortunate, and that means that even if now we have the regulations for guidelines, yeah, and they are not completely fitting for methanol. So I think that still, when you are making a methanol ship, you will have to do some risk assessments and so on, following the alternative design regulations, because otherwise it will not completely fit with the IGF code. So what do you do when you are converting a ship from regular fuel to methanol? Well, it's quite simple actually. It is a few main things, and that is that you will have to have. Well, first you can say that the tanks, you can have methanol in any tank. You're actually allowed to have methanol in the double bottom, because if it comes out in the ocean, as I said, it's not toxic. Some germs will be very happy, but otherwise it's okay. So you can have it in the double bottom, but since it is a low flashpoint fuel, you will have to have a nitrogen cover so that you won't have any explosive gases on top of the fuel. So you will have a nitrogen system, and then you will have in this case we had a high pressure system for the engine, so that means that we will have had high pressure pumps, and then when you are pumping methanol, high pressure or low pressure, you have to have double walled piping. So that is double walled piping. You have the blanketing with nitrogen, and then you have some solutions with around the tanks and so on also. When it comes to the Stena Germanica, it looked like this, that we had around we were converting a ballast tank, and then the surrounding of the ballast tank was filled with water, so that you had like a buffer zone there if there should be a leakage or something. And then we had, of course, the nitrogen system, we had the pump room, and then we had the engines here. So if we look at the safety equipment, so to say, then on this, the first that I mentioned before, that is the double wall pipes and the inert gas system. And if you look here, let's see, well, it's a little difficult to see, but here you can see actually the double wall pipe, and inside there is a high pressure pipe. In this case, that was for 1,000 atmospheres. So that looked like a gun rifle barrel actually, and then outside that you have the outside or double wall. Again, this is the methanol is not a gas, it is a liquid. So if you should have a leakage in the inner pipe, there's no expansion when it comes out to the next one. So you don't have to worry about that. And that is something that I think could be looked into a little more in coming regulations, because it doesn't behave the same way as gas pipes. If we look at the next thing is, of course, that it's difficult to have double piping everywhere. So if you could have a room where you have pumps and things like that, and that room in itself is airtight, and you have a air lock to get in there and so on. In that way, you solve a lot of the problems around this with the double piping and so on. So that is the solution that we had on Stena Germanica. Of course, you have to have a lot of monitors and sensors. So here is just an example from the machine room. We have smoke sensors, we have flame sensors, we have also methanol sensors that could detect if there would come out some kind of methanol fume in the room. And of course, that is everywhere where you are dealing with the methanol. You have to have this kind of sensors. And then, of course, to be able to get the methanol on board, you will have to have bunker station. And here we realized that there wasn't any real regulations about how to bunker methanol. So we took the initiative and make something that was called the CWA, which is a CEN workshop agreement, which is a kind of a pre standardization that is you doing in well, it was SIS here in Sweden that was helping us to do that. And there we came up with how a bunkering station should be equipped and so on. You can see here on the picture that you have a foam gun there that could pour foam out here in this area, which is walled in, and in that way you could what to say fight fire if you would have some fire here in the area. So similar things like that. Of course, a very important thing is the training. So we also developed a training program for the crew and everybody else that has to do with the methanol, like bunkering people and so on. And there, of course, we have the safety systems that I showed you, the fire alarm and the CO2 and gas alarm and things like that. And also firefighting. And there we have 3 different kinds of extinguishers. And that is the water mist, the CO2, and alcohol-resistant foam. That's about what I had time to say, I think, now. But just like that, yeah. That's our vision for the future, of course, that the methanol should come from clean sources, like water and air. Thank you.
Thank you very much, guys. This block includes 3 fuels, fuel cells, hydrogen, and the nuclear option. And on stage we have Johan Bugren from PowerCell, Katarina Westereng from DNV, and Henrik Judesen from Seaborg. And finally, Mikkel Johansson will close with a few words. So, Johan, the stage is yours.
Fire away. Yes, Johan Birgen is my name. I'm heading the marine segment at PowerCell. It's not a big segment, but we're growing rapidly. So thank you for being here today. I'm going to talk you through a bit of our marine initiative and the marine fuel cell that we have designed and developed at PowerCell. It's being adopted in a few projects. We'll talk about those as well from a safety perspective, because I was asked to do that today, more on the safety side. We're using hydrogen in our fuel cells, and hydrogen, you know, it's a bit of a tricky molecule to handle safety-wise. It's buoyant and it escapes easily, even through steel. So how we have gone about that. So here it's the basic module that we have developed is a racked solution based out of two basic modules. So it's actually going back there. It's actually two parts. The upper part is where actually the hydrogen is contained, and it's from a safety perspective, it's actually ventilated and closed space, and I will talk about that a bit later. The lower module, part of the module, is actually just the utility components that is needed to run the stack and the fuel cell. And also electronics and stuff is sitting there. We have modularized this so you can easily pull in and out these modules. They are on skids, so a little bit like the batteries thinking from that perspective. So easy service. And it's also classifiable. That's very important to know for a marine safety perspective. And I will talk a bit about the safety development that we have done. We have been part of the marine standards that are now developing for fuel cells and the use of hydrogen on board ships. So this is how it could principally look when you install a fuel cell. This is actually a superyacht project that we have been doing since roughly 2018 in the Netherlands. There's a lot of superyacht builders down there. So this is Fedship and their 3 megawatt fuel cell installation. It's not arrived in the market yet, but it's a project that will be commissioned fully next year. It's actually combined with a liquid hydrogen tank storage. So the thing you see sitting beside here is a liquid hydrogen tank containing roughly 4.4 tons of liquid hydrogen. So from a sort of a new technology perspective, this is groundbreaking technology being installed on a commercial vessel. So this is Jan van Baert talking about this on a superyacht event, the CEO of Fedship. But from a safety perspective, there is no rules for fuel cells and use of hydrogen, but those are developing now from the basis of the alternative design approach. Perhaps you will mention it a little bit later in your presentation. But it's actually that you have to prove your safety through safety assessment, FMEAs, the engineering tools that you have, safety, prove that you have a safe installation. From that, actually, now there is a circular in the SOLAS for use of hydrogen on board ships. So it's more focusing on the fuel cell rather than the fuel cell storage, the hydrogen storage. But actually, the fuel cell part is there now. So zoning principles, how to install them, and so on, is now being developed. So there's these draft rules in the market. And from that, you have those very specific requirements when it comes to zoning. You have ventilation principles, you have, or you can go for different zonings depending on if you apply ventilation to the installation or not. But so this in schematics, this is principally how a fuel cell works. Our fuel cell, the green part is where the stacks are and the hydrogen is. It's a gas-tight enclosure where we have ventilated this to high dilution. So if we have a leakage, we can dilute it to a non-explosive environment. So this would require quite high ventilation to do this, depending on your gas pressure. But this is how we go about it. You have double-walled piping going in and out of this box, so it's completely sort of sealed off from the environment if you have a leakage of hydrogen. So in the lower module, you have interfaces with process air, compressed air, and electronics. But all those ignition sources have been collected down in the support module as much as possible. So basically, this is physically how these units look. The fuel cell module is actually containing of 2 stacks, which is sitting in mirror to each other. So we have built this modularly, so you can actually extract those. And we join them together and build this unit. And then we have, in the lower casing, we have all the electronics, as I said, cooling system, so we make it easy for the ship or the naval architect to install the system. Also, we have some electronics involved, quite a lot, power distribution boxes and things. So we have a low voltage system and a high voltage system inside the fuel cell. So that enables the naval architects to have a completely sort of defined module with interfaces that they can install and follow our guidelines to have a safe installation. And this is a good basis for type approval later on. We don't have type approval at the moment, but we are working on a type approval basis. It's been a lot of educational and a lot of iteration when it comes to the safety to really get the classification societies up on board and that we are on the same page when it comes to these safety layers. So a bit of the details here. Risk assessment I've told you about. In marine terms, we call it HACCP and HACCPs. So in HACCPs, we identify the risks and we mitigate the risks in different ways. And of course, when you do these workshops, you gather a lot of clever people from different areas, and they have to qualify for being part of the workshop and being part of that very important task to build the first fuel cell and hydrogen-powered boats. So, for instance, in the FedShip project, we have gone through these very sort of comprehensive assessments. The main risks that we've identified, it's a no-brainer, of course. Small explosions, we can have big explosions, we can have fire. So those have to be mitigated by the layers of safety that we apply to the design. Then, secondly, electric shocks and obviously burns in relation to follow-up or as a consequence of the risks. Safety layers then is basically we are controlling the fuel cell with a control system. So when we see that there is something wrong, we very early on detect that for instance, in the stack voltage. We see if there's a hydrogen leak, we lack voltage, and we trip the system. That could be one thing. There is a hardware safety loop, where we have external triggers and internal triggers. So we continuously monitoring, of course, the hydrogen pressure, see that we always have a safe environment for the fuel cell to operate. As I said, limiting the number of ignition sources is very important. So we minimized the electrical components to basically be the stacks itself. They are inherently they're containing hydrogen and they are also producing electricity, so they need to be in this space. But you can actually ventilate the space and make it safe to run the stacks there. And then we put all sort of unnecessary components that we don't want in that space in another space, in the holding space. So ventilation, I talked about that as well. We're talking about a focused ventilation system that is ducted to the unit, so you have ducted ventilation connected to the fuel cell, and if you have a leakage, you take the hydrogen out from the vessel through the vent mast. And very last, I would say, perhaps not gas tight, but it's close to gas tight environment. So it can handle small explosions, but not the full pipe rupture scenario. That's always the debate whether we should have a full pipe rupture or the more mild scenario. But we have capabilities of ventilating quite some leakages, depending on the ventilation rate, of course, that we apply. So just mention a few projects coming to the market. You're now thrown in directly into the world of safety of fuel cells. What is really happening in the market could be interesting for you. I already talked about this. This is not the yacht on the picture. It's coming to I think it's going to be revealed probably to the open environment at Monaco Yacht Show next year in September. So from 1 year from now, there will be a fully functioning fuel cell there, obviously in a yacht. Then we have 2 car and passenger ferries, RoPax ferries, coming to market in 2025 earliest, I believe. And they're going to traffic from the city of Bodø to the islands of the Lofoten stretch. And this is a public ferry. Auto power off in 5 seconds. See if there's, can you see if you can click on the, maybe it's me being too inactive, I don't know. I don't mind it, but it's a bit, okay, thank you. So these 2 ferries will be basically the first of its kind trafficking commercial ferry route, fully run on hydrogen, compressed hydrogen actually, so they will be swapping storage of compressed hydrogen bottles on the vessel. 6.5 megawatts installed power. They use about 3 megawatts on the stretch when they're traveling continuously. But PowerCell is delivering roughly 13 megawatts of fuel cells. So this is by far, I would say, probably the largest order ever of fuel cells. So it's basically the same module we will apply in this project with a bit of a tweak for certain integrational aspects. But this look out for this project. It's going to be super interesting. Then we have actually a methanol to hydrogen tug in the US. And here you have an interesting safety aspect, because here you're fueling a reformer with methanol, which you're converting into hydrogen on demand, on board. And you feed that hydrogen into a fuel cell. And then we are extending this concept to make a sort of a more packaged unit where you can feed methanol in one end and you get the electricity out in the other end. So you don't need to sort of take care of the gaseous hydrogen on board. So this is very promising first installation that we do, and we will have more iterations on this. Obviously, it's a huge interest for methanol as a fuel. I mean, you're certain you talked about this earlier today already. So this is coming to the market in 2024. And this is a push tug pushing barges on the rivers in US. And actually, the owner of this and the sponsor of this project is Maritime Partners. I'm not sure if you're aware of them, but they lease tugs. They build tugs and lease them. So that's their business concept. And this, why it's called Hydrogen One, is actually that it's the first, obviously, hydrogen or alternative fuel vessel that they build, and there will be more to come in a later stage. But this is the first one. Emoji is super interesting as well, coming from ammonia. We're out. Okay, this is my last slide. Just coming from ammonia to hydrogen. Very, very interesting developments, and in Norway you have a lot of that going. So I'll leave you with that. Say thank you. And DNV next. Yes. Yeah, thank you.
Thank you. Thank you very much. My name is Katrine Westreng, and I'm Global Segment Director for Tankers in DNV. My topic today is hydrogen, and probably you know, but there are no tankers with hydrogen. So it's not the kind of my favorite subject, but it could very easily be it in close future. And if there are any good owners in this world that's going to kind of jump on hydrogen, I think we are likely to see it here in Dunse with all the technical and kind of high-spec vessels. So why hydrogen? Well, we all monitor the MEPC 80 now. We have got a marching order. We have to develop. We need to reduce emissions. And in maritime, we are going to fight with all other industries about any types of fuels, right? And we will have a mixture of the fuels as we move forward. And hydrogen could be one of the zero-emission solutions that has a promising potential for shipping. That being said, you know, the hydrogen we have today is the green hydrogen is almost zero, right? So if we are going to get to the right hydrogen, the green hydrogen, we believe that likely it will be 5% of the energy mix in 2050, right? That is 2/3 of the amount that we really need if we are going zero by 2050. So the 5% hydrogen means 200 million tons of hydrogen. And we believe that 1/3 of that hydrogen is going into ammonia, which we have spoken about earlier today, 1/3 into e-fuels, and the rest as a kind of pure hydrogen. So DNV, we are working across all kind of segments when it comes to hydrogen, the full kind of entire economy. We are working with the governments to look at their strategy of how to implement hydrogen in onshore as well as on in maritime. We have, amongst others, one of our we are a bit proud of that one. We have a huge testing facility, the Spade Adam, where we are running multi-million dollars full-scale test programs for hydrogen. We are testing out and looking at all safety aspects. For instance, how UK are going to switch from methane to hydrogen in the kind of residential area. But we are also working across all the other kind of segments like CO2, the shipping, and how hydrogen can play a role there. So if we look at the value chain, you know, when we talk about hydrogen, we talk about either blue or green. What we have today is gray or brown. It's cheap, but it's not going to save the world because it's the CO2, right? So if we are going to have the blue hydrogen, we believe that 85% of the hydrogen in 2030 is going to be blue. But that needs carbon infrastructure. And we need the governments to kind of support the whole kind of value chain. The green is coming later on, and I believe that within 35, it's going to be maybe 50-50 on the green and the blue hydrogen. Then we have the transportation. And transportation is another kind of, now I need to look at my notes here. So, you know, we can transport hydrogen in several ways. It could be liquid, it could be compressed, and we could also use liquid organic hydrogen carriers that you can use as a kind of carrying the hydrogen. But of course also you can utilize it in ammonia or the e-fuels. So when we look at the usage of hydrogen, it's a little bit difficult to kind of explain how we can use it, because you can use it direct as fuel, on the internal combustion engine. You can use it with the fuel cells, or you can use the hydrogen as building block in ammonia or e-fuels. So for the rest of this presentation, I focus on the direct use of hydrogen. Otherwise, I will go into every kind of single area here. We have a lot of challenges, and before hydrogen can be used, we need to turn all these kind of red dots into green dots, right? Availability, simply not there. Infrastructure, maturity of technology, energy density. You know, it's per today, it's small shipping. It's short shipping that could kind of use direct use of hydrogen. And then the price. I cannot simply calculate it home yet. So it's very expensive. Hydrogen, as I said earlier, and probably I don't need to go into all kind of details here, but it's the smallest molecule. And we are so afraid that it's going to escape, right? It's flammable, and it sparks with a mixture in air from between 4 and 75%. So it takes very little before it creates a danger. And of course, you need big volumes. Five times HFO when it comes to liquid, and up to 15% when it comes to compressed. So marinizing hydrogen is a challenge. In these kind of two brochures that we have made, it's a handbook for a hydrogen fueled vessel. We made that as a joint development project called the MariSafe, with also input from Norwegian government. We have also a brochure focusing on how to close the safety gap. Because, you know, marinizing hydrogen, and I think Martin this morning, he showed a picture of a gasoline station exploded in Oslo, or outside Oslo. I live 5 kilometers away from that gasoline station, and when it blew up, it felt like it was next to me. So bringing this experience to the maritime industry is very important. And then we have the kind of confined and enclosed spaces. So what if something happens? It cannot happen simply because we have the crew there and they have nowhere to expose it. And lack of a hydrogen experience also when it comes to the makers and any other kind of makers in the industry. And then finally, probably the biggest challenge of all, crew competence. How are we going to train all our seafarers according to the new fuels? So the most important here, we are really afraid of fire and explosion. It's high leakage potential, wide flammability range, low inertial energy, and then it's cryogenic. So these items are what we are kind of focusing when we are making our rules. The IGF code is focusing on segregation, double barriers, leakage, and automatic isolation of damages. It's different depending on whether you have liquid hydrogen or compressed. For instance, if you have compressed hydrogen, you have it at 230 bars. It will take you, with the leakage, it will take you 3-4 seconds. And you have a cloud of hydrogen of 150 cubes in 3-4 seconds. This illustrates how quickly. So we need to reduce the amount of leakages and make sure that they don't kind of disperse into the air. But it's lighter also, so it could go up. It depends. So we, in DNV, we are making rules. They're coming soon. The IMO do not have rules for hydrogen. They are making a guideline now. I don't believe they are going to finish this year. Next year, I believe. We do, however, have rules for fuel cells in DNV, so that's the start. But for all projects now, we need to use an alternative design process and prove equivalent safety to that of other fuels. It's a tedious and difficult project, and it takes a long time, but there are many that's doing it. And in March this year, we had Hydra, for instance. She was delivered as the world's first liquid hydrogen vessel on the west coast of Norway. Then we are running a lot of other projects with compressed hydrogen, different types of technology, different safety aspects, but the only thing we can do is to test out the new technology in order to make this fly. And then, of course, you have Gotlandbolaget in Sweden that's kind of developing the new Ropax ferry. We have some hard work ahead of us in order to ensure the proper safety, but it's coming. And then finally, I twisted my head. How could we make hydrogen, pure hydrogen, into the industry now? And the first and foremost, the business case needs to be in place. The infrastructure needs also to be in place. But then the application, yes, hydrogen is going most probably on the short sea, small vessels. It will likely be used to process ammonia and synthetic fuels as an energy carrier. And we could have, it's a type of there, hydrogen release from liquid organic hydrogen compound on board. This could be a technology that's coming quickly. Then technology, something is mature, something is not so mature. We need to work together as an industry in project in order to safeguard that we have proper technology on board of our vessels. And last, but definitely not least, we need the regulation in place. We cannot continue with the alternative design process. It's too hard, too tedious process. It's terrible for the makers, I believe, and it's we need the industry to align and not compete on regulations. That was it. Thank you.
Tack. Yes, hello, my name is Henrik Udsen. I'm representing the company Seaborg. And for those of you who might expect that I will be upstanding promoting propulsion, nuclear for propulsion, I will have to disappoint you. I'm very sorry, but that's the fact. At least not in the near future. But having had a background within ammonia and methanol for the last 30 years, it makes perfect sense to stand up here now and promote nuclear, explain about fourth generation nuclear. That is actually the building stone or the reason why talking either hydrogen or methanol or ammonia as a new shipping fuel is possible, because if you want to make it, you have to have a power source that is cheap, and that is where we come into the picture. Now, Seaborg as a company, it's a startup company, and here you have a picture of my very nice colleagues. We have now numbered to around 120 people, many nationalities, more than 25, I think. And a lot of them also with PhDs. So I have surrounded with a lot of clever colleagues, which is very invigorating. We are headquartered in Copenhagen, and what we are trying to do is to develop what we call a compact molten salt reactor power barge. So there you have the maritime touch to it as well. Now, what it is that we have taken a reactor which is using uranium as the fuel, but it's contained in a molten salt. And I'll come back to why this makes a lot of sense, especially when we talk about safety. And what we do is that we put it in a module, and we can add modules. And as you can see at the bottom of the slide, we actually put in modules where we have 200 megawatts each. So by having this set up, we can provide powers 200, 400, 600, 800 megawatt. It's not that propulsion is not nuclear in propulsion is not unfamiliar. We have examples here from the past. We have the first naval submarine back in the 50s. And then on the right, the picture on the right, top right, is the largest hangar, what do you call it, aircraft carrier, the US Gerald Ford. And then we have a Russian Navy submarine and even an icebreaker as well. And in the middle, and it's maybe most, you can say, relevant for this forum, is a commercial vessel. It was the Savannah, who was actually used as carrying goods. However, it has been decommissioned. And what characterizes all of these vessels is that it's basically owned and operated by a government entity. And even though the track record shows is quite nice, a lot of hours on the sea without any problems, we have had 2 fatal incidents with the nuclear submarines, which is most unfortunate and something, of course, which is trying to learn on. But still, this is vessels which are propulsion used from the nuclear. And nuclear, everybody says, oh, it's so expensive, oh, it's so dangerous. But the fact is, as illustrated by this slide, is that when we talk about a source for energy, nuclear comes down as one with the lowest emissions, and not the least, the most safe supply of energy. And that is why it is it's not conceivable that if we are to make a transition from fossil fuels, we will need all the resources that doesn't emit CO2 in order to do this. Whether it's wind, solar, hydro, nuclear, everything needs to be used. And the thing is, and the challenge ahead of us is, how do we use this in the most clever way? Now, this is, I've twisted this to try to accommodate for the safety aspect of this. And I think what I've learned, comparing with that, I've spent 30 years designing and licensing technology within refineries and petrochemical plants, is that with nuclear, this surmounts everything I've ever experienced before in terms of addressing safety issues. And as you can see on the right, the left part of this slide, you will see a number of headings which is mandatory whenever you apply nuclear, that you can prove to authorities that this particular design accommodates all conceivable risks related to these issues. And then some can ask, well, why do we want to develop a new nuclear technology? I mean, we have very nicely operated nuclear plants here in even Sweden and in many other places around the world. But still, safety is an issue, and that's why the technology we develop is what we call a so-called 4th generation. And the reason for doing this is, among other things, to address some of the points mentioned on the right side of the slide. So we try to make it better, not only in safety-wise, but also more efficient, more reliable, less risk of proliferation, and etc. And that is, of course, something which is done because just to increase efficiency, but also in order to hopefully also have a better perception among the public when we talk about nuclear. Now, what we do is that we have a reactor, and the reason why having this salt allows us to operate a nuclear plant in a way where it's not pressurized as it is with the conventional. And that is why the risk for a rupture or the damage caused by a rupture of a reactor is much, much less. We have shown you the 4 sizes of the reactors, and the reason for doing so is that one of the concerns many times when we talk about nuclear is that it's very expensive, it's claimed. And that is a fact, at least when it's conventional. But the approach we are taking, we are trying to modularize and put it on a barge, which means that it's supposed to be constructed in a shipyard. And if something that the ship industry is really, really known for is its ability to mass produce and to produce at the same quality and the same standard all the time. And we're trying to leverage this with this technology. Then we also have a license approach. I could spend an hour talking about the license and the obstacles we'll have to overcome, but we are trying to benefit from the IMO regulation, which is common for the entire world, and then to combine that with the rules that are applied from the IEA, the International Atomic Energy Agency. And last and not least, in terms of doing this, in order to be successful in a startup, we need partners, and we need also to be able to make a project, not the least the first one, where financing is one of the things we try to solve as well. Just to show a few things why this salt is so nice. Actually, I haven't brought with me an example today, but it is a rock when you stand with even with uranium you can have it, and it's still a rock. And the characteristic of this salt is that once it's heated up to around the 500 degrees, it will become a liquid. And only when it reaches about 500 degrees, 1500 degrees, it will start to evaporate. And that is what we're trying to utilize in the reactor. The barge, as it looks like here, we have tried to illustrate it to understand how it really works. What we do is that we actually install 2 reactors in the middle of the module. It's fueled, and then it can operate for 12 years without having to open and refuel or do anything. So the risk of proliferation, the hassle of having to handle nuclear waste is minimized. After 12 years, we will install another 2 reactors, fuel it, and then it can operate for another 12 years. So a barge lifetime will be 24 years. And again, the setup with a barge, once after the 24 years, you can tow away the barge and then put in a new barge. So in that way, we try to address some of those concerns which are typically when having to deal with nuclear. The thing is, this is the module, the middle part, and then when you add modules, that is when you get to the 800 megawatt eventually. As a startup, we cannot do this ourselves. There is an investment which is several $100 million, even billions, depending on the size of the barge. And that's why we have made a consortium together with Samsung Heavy Industries, which I'm sure all of you know, very known for their quality and ability to build very large and very intensive construction time. And then we have combined this with another very large Korean company called KHNP. It's part of the KEPCO organization. And they are one of the largest operators of nuclear power plants, not only in Korea, but also outside Korea. And with this combination, we think we have a good opportunity to provide power, not only in our area, but also not least, as someone was explaining earlier today, in areas where you don't have wind, like close to equator. It's obvious to consider also that a barge like this could be employed. Now, power is, of course, the electricity that can be provided to the grid, and that is the main and initial target, you could say, for a company like ours. But we have been talking now that hydrogen, standing here with my 2 colleagues, with hydrogen as a product to be used directly as a fuel. It can be done. We have here illustrated mainly probably to some of the smaller vessels or smaller applications. But it's obvious also to consider the 2 previous speakers from Wärtsilä and Stena in the last session, methanol and ammonia as obvious marine fuels. And in order for this transition to be sort of really credible and not least to happen in a pace that we need in order to handle this climate issue, then the power that supplies the hydrogen needs to be cheap. And this is where we come into the picture. So basically, what we're offering is a technology that we develop in Denmark. We build it in Korea, and then we intend to power the world. So thank you very much.
Thank you. Oh, that was loud. Sorry about that. Thank you all. Yeah, you can stay or you can leave. That's your call. Good. So how do we summarize this then? We had great input from a number of speakers on their specific knowledge areas, on the safety aspects in relation to new fuels that will help us meet the targets that we set out decarbonizing shipping by 2050. My summary when listening in and trying to sort of make my mind up, when we are working with how to introduce new technology and qualify new technology, we try to assess the technology in terms of, is this a known technology or is it new? And we try to assess, is this a technology that has been applied in shipping or its context, or is it a technology that is new for the context? And the first topics, when we talk about LNG, when we talk about biofuels, when we talk about batteries and methanol, I think it's fair to say and sum up that those fall into an area where we say that, yes, we have a relatively good understanding of the technology. We have a relatively good understanding of applying this technology in a shipping context. There are aspects that needs to be developed. For example, it was mentioned during the biofuel session. For example, the degrading aspect of a biofuel that we don't have for heavy fuel oil. That, of course, is new. So there for sure are aspects to address. The other part of the aspects that we talked about, when we talk about sales, yes, that's a new technology, or it's not new, it's been there for ages, but it's new the way we want to use it now, and the applications that we see coming out in the market now. Ammonia, also quite new in our neck of the woods. Hydrogen, I think it was quite clearly laid out that yes, this is an area where there is a lot of unknowns. And obviously also talking about nuclear, that's an area for commercial shipping that is quite uncharted. And we also see that a lot of safety aspects and safety concerns needs to be addressed for those kinds of fuels. I started out today's session talking about some of the safety aspects that we need to consider when we consider new energy carriers and new fuels for the shipping industry. We talked about rules and regulations, to have them in place, not to hinder, but instead facilitate development. We see that for the bulk that we can categorize as mature, yes, most probably they are in place to a large extent. However, as was highlighted, for methanol, there could be development that could make handling of methanol even easier, moving away from some of the requirements from the IGF code. It was also discussed the handling of biofuels that could also benefit from looking into the rules and regulations. And we also know that rules and regulations when it comes to implementation of batteries in other applications than small ships, or in large ships, I'm sorry, could also facilitate and speed up implementation of battery solutions for other types of vessels. And was also highlighted for the other areas where we are more in the unknown. There is a need to speed up the development of rules and regulations, not to hinder the development of technology. to me, we're looking at this, and also with the few of the backdrops that I have in the beginning of the session, I think it's quite clear that there is more effort needed when it comes to training aspects. It was mentioned in many of the presentations that training was paramount, that training material and training programs were developed and implemented, but basically all locally, project by project or product family by product family. This needs to be addressed on an overarching level in order to ensure that our business is capable and have the knowledge and capacity to take on this new technology as such. So with that, I like to conclude. I think it's been a great session. I have gained a lot of new insights. I hope that you have as well. And then, as Martin will talk more about, there is even more opportunity to learn from the discussion sessions this afternoon.
Yes, those of you who didn't get enough or want to dwell into this in a more interactive way, I strongly recommend you to go over to Safety Arena in Hall C, just to the left when you enter Hall C, where we will go into all those 3 blocks as shown on the screen right now, with a more interactive discussion per topic, led by Joachim, Daniel, and Patricio, respectively, from Lloyd's Register, ABS, and RINA. So most welcome over there, and thank you so much for your time and attention this morning. Thank you.